Hello, we are Team Humerus. I'm Courtney Mose, here with my teammates Ethan Frona, the team leader, Joe Maxud, the BSAC, Elizabeth Liu, and Sarah Edwards. We designed a periodontal bone graft and bioreactor for our client, NP Biomedical. Our motivation to do this project is due to skeletal defects resulting from trauma or other diseases remaining a major clinical problem worldwide. Over 500,000 bone graft procedures occur in the United States each year, which are most commonly periodontal procedures. The demand for synthetic bone grafts and biomaterials stems from a need to perform specific surgeries on a variety of different patient injuries. By creating a synthetic bone graft material that is relatively inexpensive, easy to fabricate, and capable of promoting natural bone growth, orthopedic surgeons can repair complex fractures using simple biomaterials. Our client, NP Biomedical, has requested we fabricate a bone graft that retains the mechanical properties of natural bone in vivo for 2 weeks. It must fill a bone gap that is 20 millimeters deep and 16 millimeters in diameter. All of this being done with a budget of $50 to make the synthetic bone graft, as well as a bioreactor device to maintain physiological conditions. For this project, we have two testable hypotheses. The null hypothesis being the average elastic modulus and ultimate strength of the calcium sulfate samples from week 0 would be the same as when compared to week 1 and week 2. The alternative hypothesis being the average elastic modulus and ultimate strength of the calcium sulfate samples from week 0 would not be the same as when compared to week 1 and week 2. Some product design specifications is that the bioreactor must be capable of maintaining biological human body conditions by maintaining a temperature between 36.1 to 37.2 degrees Celsius for 2 weeks. It must also have the capability to send the data to a Google spreadsheet with the help of a Wi-Fi chip. The sample holder must fit inside a 500 milliliter Corning jar and be able to house 9 synthetic bone samples. The bone samples must be made from a material comparable to native periodontal bone and must be 20 millimeters long and 16 millimeters in diameter. They must maintain mechanical properties similar to native bone for the duration of 2 weeks. Next, Sarah will talk about our preliminary bone sample holder designs.
Our first design is the modular disc design. This design consists of 2 discs that support the bone grafts, while a third disc serves as a stabilizing base. The 2 discs are separated by a threaded hex nut. The hex nuts help to constrain the discs to the proper distance apart and weigh down the sample holder in the bioreactor solution. This component ensures the sample holder remains stable. The rod also functions as a handle for pulling the sample holder out of the bioreactor. The next design is the plunger design. This design consists of 3 separate parts that fit together to create one sample holder system. The first part is the shell, which fits around the entire apparatus. The bottom divider consists of a plate with a rod in the middle. The 3 dividers create separate areas that allow 3 samples to be placed on one level. The additional module is a plate with 3 dividers spaced around a hole in the base. This piece allows for more samples to be added in future experiments. The third and final design is the dreidel design. This design consists of a simple cylindrical holder with a cone and rod feature that increases stability and handling. The idea of this design was to create a floating piece that holds the bone grafts on top of the bioreactor solution. The design has a conical shape to prevent it from tipping over, and the rod in the center serves as a handle. This allows the user to easily remove the device from the bioreactor. A disadvantage to this design is that it can only hold 3 samples at a time. In order to determine the best design, we evaluated all ideas with the design matrix. As a result of these scores, the modular disc design was chosen as the final sample holder idea. This design scored well in the ease of manufacturing category because it could be easily fabricated with the laser cutter in the makerspace. This design also scored well in both the ease of use and effectiveness categories because it offered an easy way to extract the device from the bioreactor through use of the rod handle and allows for the total exposure of the bone grafts to the surrounding bioreactor solution. Now Elizabeth will be talking about our biomaterial selection.
Thanks, Sarah. 3 biomaterials were considered for use as a synthetic bone graft for this project. These materials include calcium sulfate, a biodegradable ceramic with a rapid reabsorption rate, calcium phosphate, a low-cost material with similar chemical properties as calcified tissue, and polymethyl methacrylate, or PMMA, which is an acrylic polymer that forms a bone cement. After evaluating all 3 biomaterials using the design matrix, we determined that calcium sulfate was the best material. It scored well in all of the categories. Most notably, it scored well in ease of fabrication as calcium sulfate is the easiest to prepare compared to both calcium phosphate and PMMA, which requires the mixture of 2 or more materials. It also scored well in durability as it has the highest strength of around 4 gigapascals compared to the strengths of the other two materials, which is between 20 to 2000 megapascals. Calcium sulfate also scored well in the likeness to native bone category because it was found to possess similar chemical properties to native bone. The final design was not able to be constructed as a result of the COVID-19 pandemic. Had we been able to complete fabrication, the modular disc design would have been constructed for the sample holder as shown above. Also, the final electronic setup was not able to be completed. Pictured above is the circuit before further fabrication was halted. The biomaterial for the bone graft was chosen as calcium sulfate dihydrate. However, we were unable to synthesize this material. For the design of the thermistor circuit, we used a voltage divider connected to a non-inverting operational amplifier. The voltage divider is used to change the 5-volt input based on the varying resistance of the thermistor. The voltage is then amplified by the op-amp to fit the voltage between 0 and 5 volts, which are the voltages read by the Arduino. Our circuit was designed to measure between 25 to 45 degrees Celsius. Next, I will be handing off to Joe, who will be talking about the Arduino code and the NTS data collection.
Thanks, Elizabeth. The Arduino code is made to correctly interpret the voltage, giving mathematical equations from our thermistor circuit, and turn it into a temperature reading. This is done in different sections throughout the Arduino code. The main basis for runtime during data collection is timers. This allows the code to perform multiple tasks at once without delaying other code from running, as seen with delay statements. The code goes through a setup, establishing these timers and setting variables to be filled throughout the code cycle. Once setup is complete, the code starts sampling data given to it through the voltage output. The timer then ticks and various statements are called. The first to be called after every 1000 ticks or every second is check temp. This function reads and displays the temperature to the 7-segment display. Simultaneously, a call to send a warning message is also done. This function checks the stored temperature value and checks to see if it is within the given temperature bounds that we previously defined. This will then output a warning message with updated temperature to the Google Sheets. Once every 360,000 ticks, or 1 hour, the send message with temp function is called. This sends the current temperature to the Google Sheet. This cycle continues until the power to the Arduino is cut. In order to see if our biomaterial meets the specifications laid out by our client and the PDS, mechanical testing had to be done. This mechanical testing was performed by an MTS machine to find the stress and strain on parts and push them to the compressive failure. This testing was done over the course of 2 weeks with samples being pulled out and tested each week for a total of 3 times over 9 samples. While this testing was going on, the temperature of the sample solution was also being recorded. This data from the temperature and the MTS testing was analyzed in MATLAB to find the stress and strain curves, elastic modulus versus time, and along with other data to support our hypothesis of the Young's modulus and ultimate strength over time in vivo. With the data collected, stress strain curves were created for each week in MATLAB in order to determine the Young's modulus and ultimate strength to help find data and trends to help prove our hypothesis. Secondly, a normalized temperature box plot was created to see if the mean temperature was inside our previously set boundaries in our PDS. Lastly, a bar plot with standard deviation error bars was created to help demonstrate the difference between Young's modulus between weeks to further conclude on our hypothesis. All of this data was obtained from our instructors due to COVID-19. Next, Ethan will talk about testing.
Thanks, Joe. Looking back at the results from our NTS testing, it was found that the p-values for ultimate strength and Young's modulus for comparisons between weeks 0 and 1, 0 and 2, and 1 and 2 were above the significance value of 0.05. This means that there was no statistical difference in the mechanical properties over the 2-week testing period. As a result, we failed to reject the null hypothesis. The average bioreactor temperature was 37.5 degrees Celsius. This is slightly above the upper part of our range 36.1 to 37.2 degrees Celsius. Overall, this device was successful in meeting the criteria detailed in the problem statement. Our goal was to design and fabricate a synthetic bone graft that would retain its mechanical properties in vivo and a bioreactor that would mimic normal human body conditions. Mechanical testing data from the calcium sulfate samples showed that it was able to retain its own modulus and ultimate strength throughout the entire testing period. The temperature data also showed that our bioreactor was capable of maintaining a temperature close to the ideal human range of 36.1 to 37.2 degrees Celsius. Looking forward, there are three main areas where our design could be improved. First, we could have redesigned our thermistor code so we could improve both the sensitivity and the temperature output of the thermistor in solution. Also, it is possible that the acrylic material used in our sample holder could have degraded as a result of the solution. Finding a material that would be easy to fabricate and use in our bioreactor would be a next great step if given more time to work on this project. Finally, further research could be done in order to ensure the bone graft samples meet FDA standards. ISO testing would need to be done in order for this device to receive FDA approval. Team Humerus would like to thank both Dr. Puccinelli and Dr. Namunkar for directing us down the right path to make this project a success. We would also like to thank all of the TAs and SAs that were able to assist us with any questions that we had during this semester. Thank you all so much for listening.